everybody, today we're going to be looking at a visual proof of the Bolzano-Weierstrass theorem. Okay, so what does it say? It says that if we have a bounded sequence, let's say bounded by A and B, then there exists a subsequence within that sequence that converges. Okay, so in this example, I don't know, let's say x0's here, let's say x7's here, maybe, I don't know, x3 is here, and then we have, infinitely many more points somewhere over here that I can't be bothered to write down. Well, that I also couldn't write down anyway. And then what do we do with that? Well, one thing we could consider is half an interval, right? Which would be a plus b over 2, this would be the midpoint. And then if we consider those two halves separately, well, what do we see? In one half there are two terms, and in the right half there are infinitely many terms. Okay, in general this is true, right? If we have infinitely many terms between A and B, okay, we can always halve that interval, and at least one of those halves is going to contain infinitely many terms. Alright, so now let's just consider this right hand side. Okay, and I'm just going to relabel this endpoint. Instead of B, I'm going to write B1, and I'm just going to write A1 instead of A plus B over 2. Right, these are our new endpoints. And then let's just draw the points on that we had before, so that's x7, and there's some infinitely many points over here. Again, let's repeat the same process, let's do that again. Let's go halfway in between this interval, and then just pick the side that has infinitely many terms within it. Again, this is the right hand side. Okay, so here we have, well, I'll redraw the interval, the new interval that we're considering. Okay, and instead of writing B1, I'm just going to call it B2. Of course, these terms on the right are equal. And then I'm going to call this A2. Right? And again, repeat the same process. Okay, so there's some, infinitely many terms within this interval. Okay, and at least one half has infinitely many terms again within it. So maybe it's the left hand side this time. So this would be B3, and this would be A3. Right, and you just continue doing this forever and ever. And it kind of starts to look like like a tornado or something. So it's like, kind of like this, right? And then in general we have N as our left endpoint and Bn as our right endpoint. And just know that these ANs and BNs don't have to be contained within our sequence, right? We just chose them to be, halfway in between like certain intervals. They don't necessarily need to be specific terms within our sequence. Okay, and then let's choose our subsequence in a very, very easy way, right? Just pick the first term within our intervals that we see, right? So in this case it's x0. Okay, so it'd be x0, and then just pick the next term, so then move on to the next interval, and then just pick the next term, but you just have to make sure that the subscript is bigger than the subscript that you previously had. Right, so say for example if I picked, say from here I picked x24, I couldn't then pick x23 from here. I would have to make sure that the subscript is larger. But that can be done because each of these intervals contains infinitely many points. Alright? So that's how we're constructing our subsequence. But now notice two things. The ANs are monotonically increasing. And they're bounded by A and B. The BNs are monotonically decreasing and are also bounded by A and B. Right? So the ANs and the BNs converge. Okay, so the ANs and BNs converge. But, well, in fact the size of our interval is equal to A plus B over 2 to the n, right, because we're half in each term, and that goes to 0. Right, well if I just move A to the other side, I get that the BNs goes to the ANs. But they both converge, so they converge to the same thing, right? And that makes sense from my diagram. Okay, so we have that the BNs and the ANs converge, let's say, to x, right? I don't know, 2x. That may be an abusive notation a little bit, but you get the idea. right? However, we said that our subsequence, right, and I'm going to call our subsequence yn. Some people use x, and j, but I think that's absolutely terrible notation and I hate it. So I'm just going to call our subsequence yn, that we constructed, as I said before. But our yns are less than or equal to bn, and they're greater than or equal to an, right? And now, here comes the secret. Let's just take the limit as n goes to infinity, right? So we have, well, we said that this goes to x, and this goes to the limit as n goes to infinity of yn, which is, we don't know if that exists yet. But then the bn's also go to x, right? So by squeezing, the yns, which was, the notation I used for our subsequence, also go to x. So that's our proof done.
Hi guys, don't forget to subscribe to Maths.